Well, hello, amazing science students. It's me, Mrs. McMahon. Welcome to phase changes. We already learned about states of matter, and that flows very nicely into phase changes. So these are the objectives. Student will be able to identify phase changes. The student will be able to describe how energy causes phase changes. The student will be able to describe how temperature changes over time as energy is added. So, what is a phase change? And please make sure, put this on pause if you don't already have this. Your notebook is out, your guided notes are up on another tab, or they're printed out next to you so you can take notes. When you're ready, restart. You have to take notes. So, what is a phase change? A phase change is when a substance changes from one state of matter to another state of matter. Well, what were those states of matter that we just did? Solid, liquid, gas, plasma. Well, when they change from one of those states of matter to another, that is called a phase change. A phase change is a reversible physical change. Okay? A physical change, think of someone who has just lean muscle on their body. We'll say their arms, right? They just have lean muscle on their arms. And then they go to the gym and they lift weights, and their lean muscle becomes stronger and it actually becomes bulkier. They build up that lean muscle. Okay, that's a physical change, because guess what happens if they decide to stop lifting weights and going to the gym? That muscle, that bulky muscle, can return exactly the way it was. That's a physical change. And that's a reversible physical change. When we take water and we make it a solid, it's ice. When we melt that ice, it's water again, it's a liquid. If we refreeze it, if we change the energy and we refreeze it, it becomes ice again. You can take water and make it go back from ice to water and water to ice, backwards and forwards. Okay? So remember that. And that's in complete contrast with a chemical change. A chemical change is when you take a piece of wood, you cut a tree, and you season the wood, and you take a piece of that wood and you put it into a fire pit and you burn it. The ash that is left from that piece of wood will never be that piece of tree again. That's a chemical change. That's permanent. That's not reversible. Okay? So, a phase change is a reversible physical change. It requires the addition or removal of energy or a change in pressure. There are 6 common phase changes. Okay? And we have them right over here: freezing, melting, vaporization, condensation, sublimation, and deposition. Okay? So, we're just going to talk about them. That's a good graphic, though. Mrs. Caskey did well on this one. So, how does energy cause a phase change? That's ice right there, melting just on sand on the beach. Okay? So, energy is transferred between a substance and its surroundings. Energy is either released or absorbed, right? It's either let go or taken in. So, this is an example. Energy from the sun is added to the ice. The addition of energy causes the molecules of ice to move farther apart. Remember the last slideshow on states of matter, where the least amount of intermolecular forces, right, are in a solid. So they stay in that solid shape. They have a really strong attraction. And then we add the energy, and then the molecules of the ice are moving further apart. And the ice absorbs the energy and turns into a liquid. It changes its phase from solid to liquid. So, types of phase changes. Okay, he does have a fireproof glove on, but don't do this ever, even with a fireproof glove on. An endothermic change, okay? The system absorbs energy from its surroundings. So endothermic means it's absorbing, which is adding energy. So this is an example. Burning your hand on the stove. Your hand is now the system. It's absorbing energy from the hot stove. That's an endothermic change. The next type of phase change is called exothermic. The system releases energy to its surroundings. So think of exo as outside, like exoskeleton of a lobster, right? The shell of the lobster is its exoskeleton, so it's outside of its body. So when you think of the term exo, it's outside. So the system is releasing energy to its surroundings. Let's talk about that for a minute. So the system is losing energy, and an example would be soup cooling down. The hot soup releases the heat to its surroundings. If you hold your hand over hot soup, your hand's going to feel really warm. That is the heat from the soup being released into its surroundings. Okay? So remember, exo is it's released outside, and endo is absorbed. Okay, so let's talk about melting here. Poor little guy. Melting is a phase change from a solid to a liquid. The molecules speed up. The molecules move farther apart. The molecules absorb heat energy. Remember, they're absorbing, so it's endothermic. Next, we have freezing. This is when the phase changes from a liquid to a solid, so water to ice. The molecules slow down. The molecules move closer together. The molecules release heat energy. Remember, outside, releasing the heat. Exothermic. So freezing is exothermic. Now we have vaporization. The phase changes from a liquid to a gas. So that would be like boiling water. The molecules speed up. The molecules move farther apart. The molecules absorb the heat energy. Remember, they absorb, so it's endothermic. So when you boil water, at the boiling point, the vapor pressure, the pressure of the vapor, is equal to the atmospheric pressure. Okay? Atmospheric pressure is going to be different depending on where you are in relativity to the atmosphere. Okay? So evaporation. Evaporation occurs when gas bubbles are released into the air at the surface of a liquid, and it occurs at the temperatures below the boiling point. Okay? So back to the atmospheric pressure for a minute. I don't know if you've ever baked. Sorry, you can hear Wally clicking upstairs. If you've ever baked a cake or you've ever cooked something, and on the back, it's most common when you're baking. Okay, so the atmospheric pressure affects the air pressure. Okay, and you need to cook things at a different time depending on your atmospheric pressure and your air pressure, because at a higher air pressure or a higher atmospheric pressure, water starts boiling earlier. Okay, and if you use baking soda or the baking formula, like the ingredients, like flour to baking soda to salt, it's kind of thrown out of whack because of evaporation and vaporization. Okay, so look that up if you're interested. Maybe you can explain it a little bit better than I can. Hopefully, you can explain it a little bit better than I can. So here we have condensation. That to me looks like a can of soda. Okay, and it's not raining. That condensation is appearing on the can of soda. So what do you think has to happen there? Why does that happen? Well, condensation is phase change from a gas to a liquid. Well, where's the gas? The gas is outside. Well, there's gas inside soda too, but this gas is outside the can of soda, right? We're surrounded by gases. So the phase changes from a gas to a liquid. The molecules slow way down. The molecules move closer together and they release heat energy. Again, they release it to the outside, so that's exothermic. Okay, so the cold from the can turns the gas outside the can to a liquid. And if the condensation is high enough, you're going to see the condensation, you're going to see the liquid like dripping down the side of the can. Try that one day. Excuse me, but it does have to be warmer outside for that to happen. You're not going to take a can of soda outside right now and see condensation. But on a hot sunny day, something cold, right? You put it down or you're holding it and you can feel wet on the outside. That's condensation. Sublimation is something that we don't talk about very often out in our everyday worlds. Sublimation is a phase change from a solid right to a gas. Okay, the molecules speed up. The molecules move farther apart. And the molecules absorb heat energy. So remember, they're endothermic. Okay? So an example of that would be dry ice. Okay? Dry ice, you have a block of, right here, you have a block of solid ice that's frozen to a really, really, really low temperature. And you see the solid change directly to a gas. And then we have deposition. Okay, deposition occurs when a gas, it's a phase change from a gas to a solid. And that will happen when it's really, really cold outside and you look at your windows and your windows on the inside or outside in your house are covered in ice, just like this. There was no liquid. They went directly from gas to a solid. Okay, so frost on your windows, usually on your house, is deposition. The molecules slow down, the molecules move closer together, and the molecules release heat energy. Remember, if they're releasing it, it's up to the outside, which is exothermic. Does temperature change during a phase change? Think about that for a minute. Does temperature change during a phase change? So we have down here solid, liquid, gas, plasma. And the states of matter change by adding heat or energy, okay? But does the temperature change? Temperature is a measure of the average kinetic energy of the particles of an object. Remember that kinetic energy is the particle movement. So temperature is a measure of that particle movement, the average kinetic energy of the particles of an object. Temperature does not change during a phase change. So right at the point that solid becomes liquid, temperature does not change. Right at the point liquid turns into gas or becomes gas, there is not a temperature change. And right at the point gas has a phase change into plasma, the temperature does not change at those points. I'll explain that in a minute. The energy added or removed is used for breaking or making weak intermolecular forces between the particles. Remember, those intermolecular forces between the particles are what determine whether something is a solid, liquid, gas, or plasma. So this is a pretty good example right here, okay? This is simple before we add everything else in. So you'll notice that on your y-axis, your temperature right here range is, we go below 0, but our specifics are the melting point and the boiling point. And then our x-axis is heat added over time, okay? So we're going to talk a lot about time being your independent variable. Just realize that we're adding heat over time when we talk about that, okay? So we have our solid ice, and you're going to notice that as heat is added, we're going to go from a lower temperature up to 0. 0 is the melting point. 0 is the point where the ice will begin turning into a liquid. At this point, there's no temperature change. Then we're going to add more heat over time, and our liquid is going to, the temperature is going to change, the energy is going to increase. And right here at 100 degrees Celsius, where we go, where we switch over from liquid to boiling, or liquid to gas, there's no temperature change. Temperature's constant right here. Okay? But then, once our gas increases, once our gas particles, they start moving faster and faster and faster, they do that because the temperature is increasing. Stick with me here. It's going to make sense. And don't worry about writing this one down. I should have said that at the beginning of this one. This is just like a good graphic to explain. Okay? So this is what you're going to need to know here, this phase change graph. Okay? And I want you to look down here really quickly before we start. So we have temperature in degrees Celsius. We have our melting point. We have our boiling point. Melting point is 0. Boiling point is 100. And I'm not going to take my arrow and go all the way. Well, I can come over here, I guess. So if you notice here, they actually, the title isn't super accurate. The title is down here on the x-axis when the x-axis is actually time. Okay, so it's actually energy or heat added over time. So that's our independent variable, and our dependent variable is the temperature in degrees Celsius. Okay, so stick with me here. So the phase change graphs show the change in temperature over time. What type of graph is this? What type of graph should we use? Is it a scatter plot? Is it a bar graph? Is it a pie graph? Is it a line graph? This is a line graph. You need to know that the phase change graph is a line graph. So during the phase change, temperature is constant. Remember that one point where solid becomes liquid and liquid becomes gas, there's no temperature change at that point because the energy is used to break those intermolecular forces. So right here, when ice turns into water, it starts that phase change at 0 degrees Celsius. There is no change in temperature. When your liquid water becomes steam at 100 degrees Celsius, there is no change in temperature at that point because that energy has to break those intermolecular forces. It needs time to do that. So we have melting when back down again when at 0 degrees our ice cube melts into water. Okay, as energy is increased, as heat is increased over time, and as energy is decreased and heat is decreased over time, our water will actually freeze back into ice. Okay? Back up here at the top, at 100 degrees, when we add heat, we have vaporization, which means our liquid will turn into a gas. And when we cool it down, when we take that energy away, we have condensation. So once the phase has completely changed, temperature does change, as energy will cause the atoms to move more or less. So we have ice, right? We have our ice down here at the bottom, and we have an increase in energy over time, or increase in heat over time. And the temperature, these molecules are going to move more, right? It's all solid ice. Then the temperature is going to make the atoms move more again, and we have all liquid. And then the energy is going to make those atoms move more again, and we have all steam. Okay? So you can tell on this graph where all of the solid ice is, at what temperature all of the liquid water is, and at what temperature all of the steam is. And if you notice, the steam keeps increasing. Okay? So here we have a phase change graph again. All substances will have the same shape on their graph. So whether you are making a phase change graph about water or gold or table salt, the shapes are all going to look the same. But pay attention here, cool fun facts. The temperature where the phase changes occur will be different for different substances. So we know that water is going to start changing from liquid into steam at 100 degrees Celsius. If this were, nope, I don't have that one. Okay, I have melting point and freezing point. Melting point. So if you notice that the mixture of ice and water starts here at 0 degrees, right? So we're either going to freeze or we're going to melt. If this were gold, instead of it being 0 degrees, this would say 1064 degrees. So it'd be the same shape. You would just have a totally different scale. Okay? And table salt, sodium chloride, NaCl, would have a freezing point of 801 degrees Celsius. So its freezing point would not be 0. Its freezing point is 801 degrees Celsius. I wonder if there's supposed to be a negative there. Hold on 1 minute, people. Did I copy it down wrong? Oh, look at that. It is right. It's odd to see, I know I found that fact right. It is odd to see a freezing point at such a high temperature, right? So always double check your facts, okay? So same shape, but your scale is going to be completely different because gold has a melting point of 1064 degrees Celsius as opposed to the melting point of water at 0. And table salt, NaCl, sodium chloride, has a freezing point of 801 degrees Celsius. So same shape, different scale. So this is just a picture of it all put together, okay? And I want you to draw this phase change diagram into your notes because it's different than the phase change graph, okay? So I want you to take a minute and draw this into your notes. I want you to draw solid, liquid, gas, and I want you to draw the arrow of solid melting into liquid, liquid evaporating or vaporizing, those words are synonymous, into gas, and then gas condensing into liquid, and liquid freezing into a solid, okay? And then I want you to draw the arrows from solid to gas, which is sublimation, which is like dry ice. And I want you to draw the arrow from the gas right to the solid, which is called deposition. Don't worry about the word desublimation, okay? Deposition, which is like frost on your house windows. And I also want you to draw this huge line down here on the bottom that talks about increasing kinetic energy going from left to right. All right? Any questions? Please make sure you ask me. Very nicely done. Bye-bye.